Somruedee Uathawikul from Keio University. Today I will present instead of the Katsume Takumi. He cannot come to present today, so I have to present for this presentation today. So today we talk about dynamic stabilization of Hyperloop pod constrained against the DOF direction. Okay, this one is Keio ALPHA pod 3. We'll work very hard on this part and be very proud about this part. Yeah, we're proud to present this part so much. And in our pod have two parts. We have the propulsion in the rear side in the rear chassis, and we have levitation in the front chassis. So in the front chassis, we will have magnetic to magnetic for levitation, and we have 4 magnetic for stabilization. And this is the dynamic of the pod on the real. This is a picture of the force that will be the force on our pod. And to understand easier, we'll just show the levitation force, driving force, and gravity force in this picture. So next is the force applied to the pod. As you see, we have translation motion and rotation motion, and you will see we have many force in this formula. Okay, and the modeling issue, the first topic is a simple issue, a single rigid body model is simple, and the translation rotational motion is 12 ODE. Small variations of variables hold except velocity. But however, we have complex issue, many force are acting on our body, acting point and magnitude of force are complex. The force are nonlinear, functional of velocity and attitude, and especially magnetic force have uncertainty. And this is also our experiment in our lab. We have a big aluminum disc, you see picture, and we attach the rails and with the magnet and the driving motor, and then we have table to adjust the distance between the magnet and the aluminum wheel, and we have the force torque sensor unit to measure. And this is our example of magnetic force torque measurements. We fixed 2 magnets. At the first time, we fixed distance at 22 millimeters, and we rotate the aluminum wheel from 0 to 1,700 RPM. And you will see the x-axis is the time in the unit is second, and the y-axis is the force in Newton meter. At the rotation 1,700 RPM, levitation force is 20 Newton, and drag force is 4 Newton meter. So the levitation force increased to 100 Newton when the gap decreased to 10 millimeters. And next is dependency on gap. This rotation at 1,760 millimeters. So when the gap is 26 millimeter, the load will be lower than gap at 10 millimeters, as you see in the graph. And next is estimation of aerodynamic parameter. Preliminary simulations, we try to decide drag force coefficient equal 0.15, and the lift coefficient, we try to we got the value is minus 0.295. And the concluding, the long test track in the tube is necessary for our verification and validation. For the dynamic system, this is our problem that we will solve in the future. So dynamic needs to find an optimum balance of magnetic drag and levitation and other forces. And safety must be assured in the passive way. Levitation and stabilization of all directions must be provided in the passive way. So that's all for today. Thank you for your listening.
Thank you. Any questions? So I'd like to mention that the pod is actually for display. It's going to be on display for the during the reception and the poster session in the evening. So I will encourage you to kind of contact, ask all the questions with the copy in front of you. Thank you so much.
Thank you.